This is our final video for reaction equilibrium, and today we're going to look at the reaction quotient Q. So here we have an equilibrium problem. We've got a reaction occurring, hydrogen and fluorine gases reacting to make hydrogen fluoride, and we're given the value of KEQ, and we're also given the initial concentrations of both reactants and the products. So what I've done is I started a little ice table here. So we're looking at concentration of hydrogen, fluorine, and HF. The initial concentrations were given, so I've got those filled in. And now we're faced with this question where we need to figure out which direction this reaction is going to shift in order to reach equilibrium. Is it going to be shifting to the left, or is it going to be shifting to the right? And we need to figure that out. Previous questions that we looked at had a situation like this, where we've got nothing of something, and so we know that the reaction is going to shift in the direction of nothing. And in this case, since we have reactants and products all present, we need to do a little mathematical test to tell us which way the reaction is going to go. So what we do here is we calculate Q, and it's the reaction quotient, and it is a test. Okay, so this is a test that we do with the numbers to check and see how close we are to equilibrium and what direction we need to go to reach equilibrium. So to calculate Q, we set things up the same way as if we're calculating the equilibrium constant. So in this case, the concentration of HF squared divided by the concentration of hydrogen, and the concentration of fluorine. Now, this is exactly the same as the equilibrium constant expression. We're doing a test though. We're doing a test to see whether this value is equal to the KEQ we were given, which is 115, or above 115 or below 115, to tell us which way the reaction is going to go. So we've got 3 squared divided by 2 moles per liter times 2 moles per liter. And what we get for Q is 2.25. So Q is 2.25. And for this equation, KEQ we said was 115. So, what has this test told us? KEQ is bigger than our Q value. So in order to reach equilibrium, this value needs to go up. Okay, so it's got to go up from 2.25, where it is, to 115. So if that value is going to go up, if we need to increase this value, that means we need to increase the amount of HF that we've got, make our numerator bigger, and our denominator a little bit smaller. So it's going to tell us the direction that the reaction is going to go. So in order to make this fraction bigger, we need more HF, and we need less hydrogen and fluorine. Okay, so this is the thing that makes this question different from previous ones, is we need to do this little test to help us see the direction the reaction is going to take. After that, we proceed the way that we have been. So on the reactant side, we know the amount of hydrogen and fluorine are going to decrease by some value x, and on the product side, HF is going to increase by some value 2x. So at equilibrium, the concentration of hydrogen is 2 minus x, the concentration of fluorine is 2 minus x, and the concentration of HF is going to be 3 plus 2x. Alright, I know I dropped my significant digits there. I did that for space sake, so we'll get them back in a second. So let's solve for x. So KEQ, we know, is the concentration of HF squared divided by the concentration of hydrogen divided by the concentration of fluorine. And we'll substitute in our equilibrium values. And that means we've got HF 3.00 plus 2x squared divided by 2 minus x times 2 minus x. KEQ. Alright. So this is great. We can simplify this. In the numerator we have 3 plus 2x squared. In the denominator we have 2 minus x times 2 minus x. So that's 2 minus x squared. So we can find the square root of both sides. And I didn't put my KEQ in there, so let's do that. It was 115, yes? Yeah. So 115. So we can take the square root of both sides, and we can avoid quadratic equation. So the square root of 115, I've got 10.72. In the numerator, 3 plus 2x. In the denominator, 2 minus x. And now we can solve for x without too much trouble. Alright, so when it gets to this step, just make sure that you're careful, that you're collecting like terms appropriately and not making any errors with negative signs. Don't be lazy. So 21.44 minus 10.72x equals 3 plus 2x. So I'm going to collect my x's on the right. 4 minus 3. I've got 18.44, and over on this side 12.72x. So x is going to be equal to 18.44 divided by 12.72, and we get 1.45 as our value for x here. So that's looking pretty good. Now we can find the concentrations. Let's look back up at the question way up here. So we want to find the concentration of all of the chemicals at equilibrium. Okay, so x is 1.45. I'm just going to bring it back up here. 1.45. So the concentration of HF is equal to 3 plus 2x. So that's 3 plus 2 times 1.45. 1.45. So that'll be 5.9. And the concentration of hydrogen is equal to the concentration of fluorine. Is equal to 2 minus x and we get 0.55 moles per liter. So if you take these values and sub them back into your KEQ expression, we should end up with 115. So what has happened here is initially when we substituted the values in, we got this value that was much lower than KEQ, and then the reaction shifted to reach equilibrium, and now if we sub those values in, we will get 115 for our answer. You can try more questions around page 461 in your text that involve doing that Q test before you solve for the equilibrium concentrations.